we go.
Hello, and welcome to this series on creating your own block-based sandbox game. My name is John Wagner, and I'm excited to take this journey with you. In each of the upcoming modules, I'll take you step by step through the process of programming this great game. When you're finished, you'll be ready to tackle the challenge of adding your own custom content and programming. I also want to point out that we'll be discussing why we do things, not just how to do them. Through this experience, you'll add knowledge and skills that will help you create games you design yourself. Before we get started, let's take a look at the objectives for the course. For our course objectives, we'll develop an object-oriented hierarchy using inheritance that will allow us to quickly add new blocks to our game. We'll identify areas in game development where inheritance will lead to a more generalized, robust, and extensible solution. We'll learn how to use a line trace, which is a very important programming technique. We'll learn how to use animation assets to add visual appeal to our game. In this module, we'll get an overview of the level that our game will be built in. We're going to use the assets and character from the Unreal Learning Kit, which is a great collection of assets available for free on the Unreal Marketplace. By using this kit, we'll start off with a great-looking game right out of the gate. Our objectives for this module are to explore the starter project and become acquainted with the included content and folder layout. We'll adjust the lighting for the level, and we'll also move the assets around in the world outliner to neaten up the project. We'll create some folders for the assets that we'll be creating in the game as well. To create the project, you'll need to download the Unreal Learning Kit. To do that, open the Epic Games Launcher and select Marketplace from the Unreal Engine sidebar selection. In the Marketplace, go to the search bar and type in Unreal Learning Kit. The Learning Kit is free, but you'll need to add it to your account by adding it to your cart, selecting the shopping cart, and checking out from the Marketplace. Once you've added the Learning Kit to your account, select the Learning Kit in the Marketplace again, and select Create Project. Create the project and open it from the library in the Epic Games Launcher. When the project first opens, select the Show Sources panel on the left of the content browser. To find the
All right. I think we're
I'm
caught
gonna
up.
select the
hop off.
the
What? Okay. Take care, Mer.
Epic Games Launcher left of the content browser. Project first opens, select the Show Sources panel on the left of the content browser. To find the block game map, navigate to the block game folder content browser. When the project first opens, select the Show Sources panel on the left of the content
Oh,
browser.
okay. That's what I already
To
have.
find the block game map,
Oh.
navigate to the block game folder and find the maps folder. Double-click on the block game map to open it. Since the block game map is the map we'll always want the editor to open while we create the game, open the project settings from the Edit menu. On the left side, choose Maps and Modes, and then in the Editor Startup map, click the drop-down and select Block Game Map. Do that for the game default map as well. Close the project settings. The layout of the project is such that the Learning Kit assets are in the Learning Kit Games folder. I'll toggle that open now. Although we'll use some of the Learning Kit content later, we'll add our content to the Block Game folder. Open the Block Game folder. There are subfolders here with the content that we'll use. We'll make some additional folders in a moment as well. To get a feel for the included character, click the play button on the toolbar. You'll see the Learning Kit character. This character has several animations attached to it, as well as interactions with the left and right mouse button. When the middle mouse button is clicked, it does a celebration. We use a character based on this character, but we'll modify it to place blocks in our level. Also, our character uses a modified skeletal mesh with a socket to attach a block to. To see the socket, go to the Player Character folder and open the SK block character. To see the socket, go to the Player Character folder and to attach a block to block character. To see the socket, look in the left panel for the skeleton tree for the block socket and click on it.
Where'd you go? Thanks for the mer. Not the mesh. No. Oh, skeletal tree. Got it. Nice. Clavicle. Done. 3. No, we don't have that.
For the skeleton tree for the block socket. See the socket, look in the left panel for the skeleton tree for the block socket and click on it. You'll see that that socket is attached to the thumb of our character. We'll make use of this later in the project.
What if mine's not there? I don't have it! Please show. Add socket. Sure. What do you call it? Block socket. Okay. Looks like it's about the same, so it's probably fine.
Of our character. We'll make use of this later.
Oh, maybe we should show scenes. I don't think that's relevant. Default non-linked layers. Okay.
Later in the project. Close the SK block character. The level template includes a directional light called light source that we can customize by pressing Ctrl L and moving the mouse around. Set the lighting up to your liking. I'm going to leave it set to a fairly bright daytime scene. Also observe that there's a player start in the level right there, and we'll leave that right where it was when we started. In the world outliner, you'll see all of the assets that are included in this level. You might notice that it has several folders and the folders are open. Let's toggle those closed by clicking the small triangle to close each folder. That'll neaten things up a little bit. We're also going to create our own folder in just a second to move some of the content. You'll notice all of the assets preceded with VFX are visual effects. Let's make a folder for those and move those into it. In the world outliner, right-click in a blank area, select Create Folder, name this folder Visual FX. Select the first VFX Mesh Clouds base, Shift-select the last visual effects asset, and drag that into the visual effects folder.
Other way's
and
faster.
toggle that folder closed. Let's finish setting up the folders for our game. Go to the top level block game folder,
I have stuff
and
you
then
don't.
in the content browser, right-click, go to the top
What do I have that you don't? UN instance foliage. Player service guide. Interesting.
level block game folder, and then in the content browser, right-click and select New Folder, and name the new folder Blueprints. Go into the Blueprints folder, and make another folder by right-clicking, selecting New Folder, and name that Blocks. Back in the block game folder, we'll make another folder by right-clicking, selecting New Folder, and naming that folder UI. Let's take a look at some of the other included content. In the Materials folder, there's the materials for the blocks that we'll create, including the textures that were used to make those materials. In the Meshes folder, there's a static mesh called Block, and this is the block that we'll use for the basis of most of the blocks in our game. We already saw the Player Character folder, and inside of the Player Character folder is an Animations folder with 2 animation montages set up for us to use in the game as well. The Sounds folder has some sounds to use in the game, and we'll further add material to the UI folder. Notice in the Textures folder, there's a crosshair that we'll be using for our user interface later. To review, in this module, we explored the starter project and became acquainted with the layout. We set up the lighting for the level, and we modified it to meet our design needs. We also organized the world outliner, and then we created some folders for the assets we'll create for our game. I'll see you in the next module. In this module, we'll create the blueprint for the base block, which is the parent class for all blocks in the game. Our objectives for this module are to create the parent class for all blocks in the game. We'll modify 3D coordinates in local space to account for different points of origin. We'll also modify collision presets, and we'll write a function that correctly calculates where to place a new block when a player clicks on any of the sides of an existing block. To get started, locate the Blueprints folder in the Block Game folder. In the Content browser, right-click and select New Blueprint Class. Select Actor as the parent class. Name the new blueprint BP_base block. The base block blueprint will be the parent class for all blocks in the game. As such, we'll add the components and functionality to this actor that all the blocks in the game will need. Open the BP base block. To add a component, click on Default Scene Root and select the Add Component button. Type in Static and then locate Static Mesh Component button. To add a component, click on Default Scene Root and select the Add Component button. Type in Static and then locate Static. To add a component, click on Default Scene Root and select the Add Component button. Type in Static and then locate Static Mesh. Change the name of this to Block Mesh. In the Details panel, select the SM_block as the static mesh. Scroll down and find the collision preset and change it from block all dynamic to no collision. The reason for this is we might be using static meshes later that won't be perfect cubes, and we'll have to account for that. So we'll let the static mesh be the visual display of a block, but we'll add a collision to handle the collisions of the block. We also have to account for the fact that the default scene root is in the center of the block, and we want the point of origin of the block to be in its lower left-hand corner over here. So we'll have to change the location in local space of this static mesh. To do that, make sure that the block mesh is selected, go to the transform, location, and change the location to 50 units for each of the 3 axes. You can now deduce that our block is 100 units cubed, and that the center of it was at 50 units. By offsetting at 50 units in all 3 axes, we've moved the point of origin of the mesh to the lower left-hand corner when we use it as a blueprint. Let's click on Default Scene Root and add the collision. Come up to Add Component, type in Box, and select Box Collision, and change the name of that to Box Collision. Observe that the box collision also has its point of origin in the center, and we need to position that so that it completely encompasses our cube. First, let's change the size of it. Box collisions use what's called an extent, and an extent specifies the radius of the block. So in the x-axis right now it's set to 32. We're going to change that to 50 for each of the 3 axes. And then we're going to offset the location of the box collision in local space to 50, 50, 50 as well. You can now see that the collision completely encompasses the box. We have to modify the box collisions preset. So go find the collision preset for the box collision and change it from overlap all dynamic to block all dynamic. That way things won't be running through our blocks. All of the blocks in the game will share a variable. So we're going to add a variable by going to the My Blueprint panel, clicking on the Add Variable button. And this is the variable that indicates whether or not a block is breakable. And a good name for that would be isBreakable. And the type should be Boolean, true or false. Click Compile after adding the variable, and then click the checkbox to ensure that the isBreakable variable has a default value of true. The last step to creating the BP base block is to write a function that will calculate where to place a block if the player clicks on any one of the sides of an existing block. Now let's look at the layout of the block. The x-axis proceeds forward like so, y-axis in a positive direction to the right, and z-axis goes upwards in a positive direction. The sides of the block are what's called its normals, and the normals have a direction. The normals for the x-axis are -1 on this side because the x-axis is going in the negative direction, and on the opposite side, it's going to be +1. Now, normals are specified with an x, y, and a z, so if we click here on this block, our normal would be -1 in the x, 0 in the y, and 0 in the z. Conversely, on the other side, it would be, if we click here, it would be +1, 0, 0. And if we click on the y-axis, it will be 0 in the x, 1 in the y, and 0 in the z. And if we clicked on the top, it would be 0 in the x, 0 in the y, and 1 in the z. We're going to make use of this in just a second. That's why I'm taking the time to explain it. So let's write the function that's going to calculate where to add the next block if somebody clicks on this block. The idea is if we click, say, on this face here, we'll return the coordinates in the world of this location where the next block should be placed. To add a function, click on the Add Function button, and let's change the name of this to getAttachLocation. The getAttachLocation function is going to need 2 parameters to do its work. It'll need the location in the world of where the click occurred, and it will also need the normal of the block that was clicked on. We'll add those by going to the input section, clicking the new parameter button, and let's change the parameter name to click location, and that should be a type vector, an X, Y, or Z value. Let's add one more parameter, which will be the normal, or the direction the face that was clicked on is facing, and that will also be a vector. When the get attached location function is done, it will return an output. So we'll add an output parameter, which will be the attached location, and that will also be a vector. In between the start of the function and the end, we'll do the math to figure out what the attached location is. I'm going to walk us through the nodes for this, and I know I promised in the beginning to provide information on why things are done a certain way. We're going to circle back to this function in a later module, so I'm just going to show you the nodes for this so that we can get through this part and get to the part where we start adding blocks, which is really fun. So the math looks like this. We're going to drag off the click location, press plus, and do a vector plus vector, and add the normal to the click location. We're then going to drag off of the sum of those two vectors and type minus, and add the normal to the click location. Do this. We're going to drag off the click location, press plus, and do a vector plus vector, and add the normal to the click location. We're then going to drag off of the sum of those two vectors and type minus, and vector minus float, and type in 50 here. We're going to subtract 50 from each of the three axes in that vector. We're going to take the result of that, drag off of that, and we're going
Alright, where is this? Vector man. Oh, I bet it's the stupid context. Oh, I've gotta be missing something.
the sum of those two vectors and type minus, and vector
Vector. Vector. Okay. I'm guessing that they changed it to something else. You need to convert the inputs manually. Unfortunately, when you right click the bottom pin, convert to float. What the heck was I referring to? process. 437. It's so many comments here. I don't know which comment they're referring to. By which, okay, maybe. Video unavailable. Awesome. Cool. That's super useful. Okay. To phone mass nodes and multiple versions taking different time, but change to a single node that takes wildcards. The UI is variable at the same time. To use one other. Try. How do I actually just be like, yo, hey. Okay. Subtract. Promote variables. Convert pin. Ah. There we go. What did I say? 50?
Vector minus float, and type in 50 here. We're going to subtract 50 from each of the three axes in that vector. We're going to take the result of that, drag off of that, and type snap, and select vector snapped to grid. And for grid size, type in 100, the size of the grid that we're building our world with. That will be our attached location. Connect the return value of that to the attached location. Again, we'll circle back and explain how this math works in a later module. So that's it for the getAttachedLocation function. Click compile and save.
Okay, there we go.
And close the getAttachedLocation function. You can close the BP base block. And let's review the objectives for this lesson.
Okay, that's annoying.
Block. And let's review the objectives for this lesson. In this lesson, we created the parent class for all blocks in the game, the BP base block. We applied 3D coordinates to local space to account for different points of origin. Finally, we wrote a function that correctly calculates where to place a new block when a player clicks on any of the sides of an existing block.
Hey, Stormy.
I'll see you in the next lesson.
How you doing, Stormy? Hope you're well.
In this module, we'll build our first specialized block, which is the foundation for the level. That'll be the floor. The floor will be a child class of the BP base block and use the materials from the BP base block. It will also be unbreakable. Our objectives for this module are to write a sequence as part of a construction script. We'll create an instant static mesh with similar properties as a static mesh. We'll utilize a nested for loop, or a loop inside of a loop. We'll use
Wearing in your pin badger with big fluffy tail made eye contact with skin. Silly Stormy. Hi, Stormy.
instance editable variables to control the size of the floor actor. To get started, find the BP base block blueprint in the Blueprints folder. Right-click on it and select Create Child Blueprint class. Name the new blueprint BP_floor. Open the new blueprint for editing. By creating a child class, our new class will inherit all of the attributes and data of its parent class as well as any functions, like the getAttachedLocation. By using the object-oriented mechanism of inheritance, we can make use of the components and functionality of the parent class and specialize
It's pretty close, Stormy.
the child class in a way that makes sense for it. And specialize the child class in a way that makes sense for it. Let's make sure that the floor is not breakable. So we'll need to see our parent class's variables. In the My Blueprint panel, click the drop-down and select Show Inherited Variables. You can then open up the Variables panel, select the isBreakable value. You can then open up the Variables panel, Show Inherited Variables. You can then open up the Variables panel, select the isBreakable value, and then uncheck the isBreakable value so it's false, and click Compile. Now we'll add the components that this class needs. Select the default scene root, click on the Add Component button, and search for Instanced Static Mesh. Name this Instanced Block Mesh. We'll use this block to dynamically create instances of the block used for the floor. This is much less expensive in terms of memory and rendering than if we use several instances of the same static mesh. We need to add two variables to control the size of the floor. Click the Add Variable button and name the first variable Floor Size X. In the Details panel, change the variable type to integer. Click Compile, and set the default value to 20. The floor size y will be the same as the floor size x in its default value, and it will also be an integer. Because of that, I'm just going to select the floor size x and click Ctrl-W and change the name of the variable to floor size y. Click the Compile button, and you'll see that the default value is also 20. Another change we'll make to the floor size x and the floor size y is we'll make them instance editable.
So if you got sprayed, your life would be sprayed. Oh! Oh, that kind of fluffy tail. Oh! Yep! That's a different kind of fluffy tail than I was thinking. Yep! And yes, streak.
So in the Details panel, click on Instance Editable for floor size x, select floor size y, and make that instance editable as well. And click Compile. Size y panel, click on Instance. We'll make them instance editable, which will make to, and you'll see that the default value is also 20. Another change we'll make to the floor size x and the floor size y is we'll make them instance editable. So in the Details panel, click on Instance Editable for floor size x, select floor size y, and make that instance editable as well. And click Compile. That will expose the variables in the editor so that we can change the size of the floor in the editor rather than come back and modify the blueprint. And when we make multiple instances of the floor, we can make them with different sizes as well. We're now going to edit the construction script. Click on the Construction Script tab to open it. In the Construction Scripts graph, if you don't see a connection from the Construction Scripts entry node to the parent's construction script, right-click on the Construction Script node and select Add Call to Parent Function. Then link those two nodes up. This will call the parent's construction script. This
To me, since he was ready to use it.
is useful in the event the parent construction script has code that should be run before the child class is created. If you've used other object-oriented programming languages, such as Java, this is analogous to calling your superclass's constructor explicitly. Now, in this particular example, the parent's construction script doesn't do anything, but it might in the future, and you probably want to call it from all of the classes that inherit from it. The first bit of code we'll add will be to snap the actor location to a unit of 100. This will ensure our math works for the getAttachLocation function in the base block. Right-click and type get actor location and select the get actor location node. This returns the location of the actor.
Yarg!
Luke fattened 1 critters. I once submitted 10 puns to a joke competition. I really thought with that many, one was sure to be a winner. Sadly, no pun intended.
Oh. God dang it, Yarg. Oh. Uh-huh. How you doing? Hope you're well. Rinse and repeat!
Luke fattened 1 critters. I once submitted 10 puns to a joke competition. I really thought with that many, one was sure to be a winner. Sadly, no pun intended.
Oh, it almost hurts. Yep. Yep. Yes, it does. It's great that it actually read it very well, though.
Actor in world space. Drag off of the return value and type in snap and select vector snap to grid. Set the grid size to 100. Drag off of the return value of the vector snap to grid and type in set actor location. Hook that up to the parent construction script. For this to work correctly, we need to make sure the construction script doesn't run when the actor is dragged in the level. Go to the class settings and under the blueprint options, uncheck Run Construction Script. On drag. Print options, uncheck. Go to the class set, the construction script doesn't script. For this to work correctly, we need to make sure the construction script doesn't run when the actor is dragged in the level. Go to the class settings and under the blueprint options, uncheck Run Construction Script on drag. Use a sequence node with 3 nodes to help organize the code. Press S on the keyboard and left-click to bring up a sequence node. We'll use 3 execution pins for our sequence node, so click the Add Pin button to add the third.
Character Mars, day 5, let's go, proceeds to install lurk. Thanks for the lurk. Yeah, technically should be internet list now as of an hour and a half ago because router's not there, but so yeah, it could be better. Oh, okay. It's in like you're supposed to be getting a new router, but that hasn't arrived yet. Claws crossed for you.
1. Hook up the sequence node to the set actor location. On sequence wire 0, set the static mesh of the instant static mesh component to the same sequence wire 0. Hook up the sequence node, so click the Add Pin button to
got
add
it.
the third one. Hook up the sequence node to the set actor location. On sequence wire 0, set the static mesh of the instant static mesh component to the same static mesh as the superclass. To do this, drag out the block mesh, drag out the instance static mesh, and drag off of the instance static mesh and type in set static mesh. To get the static mesh from the block mesh, drag off of the block mesh and type in static mesh and select get static mesh and hook up the return value of that to the new mesh. Also make sure you hook up the sequence for 0 to the set static mesh pin. And static mesh and select get static mesh and hook up the return value of that to the new mesh. Also make sure you hook up the sequence for 0 to the set static mesh pin. We can now destroy the block mesh component because we won't be needing it anymore with this class. Now destroy 0 to the set.
Okay, block mesh, target, instant. Instance block mesh goes to target. Block mesh. Okay. Stormy, it all makes sense now. I'm glad. Alright, just hoping it's not just the post service using a new, more modern notification system instead of the old SMS message, because if that's the case, your old cell phone might not be able to receive them. Oof. Stormy, you totally get this whole programming thing. Yes! Good!
Static mesh pin. We can now destroy the block mesh component because we won't be needing it anymore with this class. So drag out another block mesh, drag off of it, and type in destroy component, and hook that execution pin to the set static mesh pin. On sequence wire 1, we'll write the code to build the floor. We're going to use a nested for loop, which is a for loop inside of a for loop. Drag out of sequence 1 and type in for loop. The first index should be 0. The last index should be the floor size x minus 1. I'll explain in a minute. Drag out the floor size x and select get floor size x. Drag off of the floor size minus 1. I'll explain in a minute. The first index should be 0. The last index should be the floor size x minus 1. I'll explain in a minute. Drag out the floor size x and select get floor size x.
Oh, I know what they're
Drag off
doing.
of the floor size x, type in a minus symbol and select minus int and use the default value of 1 and hook that up to the last index. The reason we're subtracting 1 from the floor x size is that the floor x size has a value of 20 by default and the first index is 0. That's 21 numbers, 0 through 20. We want 20 for the entire number of blocks. So 0 through 19 would be 20 floor blocks. So we have to subtract 1 from the floor x size. To the person creating the level, it wouldn't make sense for them to specify 19 and get 20 floor blocks. So we do that math for them here in the construction script.
Okay. I don't know what the standard is for a situation like this, but do what I can. No, not you. Let's see how this goes.
We're going to use the index of the loop body to help us figure out where to put the block in the x-axis. So right-click on the index and select Promote to Local Variable.
Oh.
Local variables appear in a different location than blueprint variables, and they're local to the script that they're in. Name the new local variable x. Hook up the execution wire to the loop body. From that node, drag off the exec pin and type in for loop again. And for this for loop's last index, we'll use the floor size y. As a shortcut to getting a variable value, hold down the control key and drag the variable out. Once again, reduce the value by 1. So type in a minus sign, int minus int. Use 1 for the value and hook that up to the last index. We'll promote the inner for loop's index to a variable as well. Right-click and select Promote to Local Variable and use the name y. Hook up that execution pin. All that's left to do is to add the instance of the instance static mesh and calculate where it should go. Drag out the instanced block mesh. Drag off of the instance block.
No. I don't think I like that at all. We're going to keep it like this. Because this is going to come out here. We're going to deal with that. Alright, and what was this instant block mesh?
Block mesh and type in Add Instance. Hook that up to the Set Y execution pin. To create an instance, we need to have a transform, a location, a rotation, and a scale. We're only going to furnish the location. Right-click on the instance transform and select Split Struct Pin. We're going to calculate the X, Y, and Z, so we'll be setting them independently. Right-click on the instance transform location and select Split Struct Pin as well. This will give us access to all three of those values. The Z value will always be 50, as we're offsetting all of the blocks by 50 units to make up for the fact that the point of origin of the blocks is in the center of the block. Get the X from the local variables and the Y as well. These will hold the value 0 through whatever the last index is. We'll multiply that value by 100 because each block is 100 units cubed. So drag off of the X, type in a multiplication,
That's weird. Why
and we're going to use int times float because the instance transform location is a float. This will convert the integer X to a float when we multiply it by a float, which is going to be 100. Duplicate this node, select it and press Ctrl W, and hook up the Y value. We have to offset these by 50, again, to account for the point of origin difference. So drag off of the product, type in plus, and select float plus float, and use 50 for the other value. Duplicate this node, Ctrl W, and hook in the product of the Y times 100. You can now directly connect the X value and the Y value. To check if this is working, click Compile, go into the viewport, and have a look at your 20 by click.
X, Y. Oh, it's that. Curious. Convert to float. Now it doesn't have to convert. Just do this. No. Integer to a double. Return value integer. Convert to float. Float.
We're going to use int times X, type in a multiplication, and we're going to use int times float because the instance transform location is a float. This will convert the integer X to a float when we multiply it by a float, which is going to be 100. Duplicate this node, select it and press Control W, and hook up the Y value. We have to offset these by 50, again, to account for the point of origin difference. So drag off of the product, type in plus, and select float plus float, and use 50 for the other value. Duplicate this node, Control W, type in plus, and select float plus float, and use 50 for the other value. Duplicate this node, Control W, and hook in the product of the Y times 100. You can now directly connect the X value and the Y value. To check if this is working, click Compile, go into the viewport, and have a look at your 20.
Curious. Doesn't make sense, Risha. From double precision to integer. But that's just gonna do that. Wow. Current value 100, which on B's valid X with valid number. Integer property. Huh. I feel like I'm doing something wrong. This tutorial is written for a different version. So, hi Griffin food, bye Griffin food. By 100. Duplicate that. You go here. And that is very much the wrong ad. $50. So we'll do the conversion there. I feel like it's wrong, but I feel like there's a better way to do that. But we'll
by 24. Go into the viewport.
Oh, dude, look at that. Okay, that's kind of cool.
Have a look at your 20 by 20 floor. Now that the floor is created, we have to adjust the box collision so it will cover the entire floor. In the construction script, drag out the box collision component. Drag off of the box collision and find the Set Box Extent node. Hook that up to sequence wire 2. I'm going to reposition the nodes a little bit to make it easier to do that. For the value of the box extent, right-click on it. Hook that up to sequence wire 2. I'm going to reposition the nodes a little bit to make it easier to do that. For the value of the box extent, right-click on it and select Split Struct Pin. This allows us to adjust the X, Y, and Z separately. We'll know that the Z is going to be 50. Recall that the box extent is a radius extending out from the center of the box. To calculate the X and the Y, we'll use the floor X size and the floor Y. So drag those out and get them. Again, holding down the Control key to do a get. And we'll multiply those times int times float by 50. I'm going to duplicate that node, Control W, hook up the floor size Y, and hook those up to the box extent. And that will cover the size of the box extent. Now observe that it is not in the correct location yet. We have to move it to the center. To do that, drag out another copy of the box collision component. And type in set world location. To calculate the world location, we'll make a vector and we'll add the current actor location to that. So right click and type in make vector. We'll use the calculated center point of the box collision. So the X goes into the X, the Y calculation goes into the Y, and Z is going to be 50. So this tells us the location in local space. Right click, get actor location, and drag off of the make vector plus vector, and add the offset in local space to the current actor location and connect that to the new location. Actor location.
Location. This. That.
And connect that to the new location. Make sure your code is compiled and saved, and then go back to the block game map. You can now drag an instance of the BP floor out and change.
God dang it.
Make sure your code is compiled and saved, and then go back to the block game map. You can now drag an instance of the BP floor out and change its size using the default variable values. So for floor size X, we have 20. We can change that by clicking and typing a new value or dragging slowly. Don't go too crazy with the floor X size and the Y size yet. And you can also reposition and observe that when you reposition the floor, it is snapping to the grid units of 100 by 100. I'm going to lower that down in so it just rests right on top of this island. And it looks like I made the floor size Y just a little bit too wide. There we go.
What did they
23
say
looks
about
pretty good.
snapping?
It's right above 100. You reposition, and you can also reposition and observe that when you reposition the floor, it is snapping to the grid units of 100 by 100. I'm going to lower that down in so it just rests right on top of this island. And it looks like I made the floor size Y.
No, it's
Observe
not.
that when you size yet. Don't go too crazy with the floor X size and the Y size yet. And you can also reposition and observe that when you reposition the floor, it is snapping to the grid units of 100 by 100. I'm going to lower that down in so it just rests. And observe that when you reposition the floor, it is snapping to the grid units of 100 by 100.
No, even yours isn't,
lower
dude.
that down in so it just rests right on top of this island. And it looks like lower that down in so it just units of. Observe that Y size yet. And you can also reposition and observe that when you reposition the floor, it is snapping to the grid units of 100 by 100. I'm going to lower that down in.
Oh, okay. Snaps, but... Wait. What? Oh, I'm so confused about that thing. Shock! Okay, I don't get the whole... I mean, we're snapping to tens, but that's because of another reason. Oh! Oh, it's when I let go. Oh, I have to let go. Now it's not. Oh, okay, I'm being a derp. I didn't even notice that it was snapping as soon as I let go. Got it. Okay, cool.
And so it just rests right on top of this island. And it looks like I made the floor size Y just a little bit too wide. There we go. 23 looks pretty good, and 27 in the X.
23,
In this module, we wrote a construction script for the floor using a sequence and the nested for loop. We created an instance static mesh with similar properties as a static mesh. We applied instance editable variables to allow us to modify the floor in the editor.
Neat.
In this module, we'll add the essential pieces to make a playable game. We'll create the HUD, which is going to be a crosshair, so the player can see where the next block will be placed. We'll also add a player character and a game mode, which are essential pieces to create a playable game. Our objectives for this module are to create the HUD to display the crosshair. We'll assign inputs to control player movement. We'll create a player character and write blueprint code that responds to the inputs. Finally, we'll tell the game to use our new player character by creating a game mode. To get started, go to the UI folder, right-click in the content browser, and select Blueprint class. We'll need to search for the parent class, so toggle the All Classes list open, and then type in HUD. Select HUD for the parent class. Change the name of the blueprint to HBP_crosshair, and then open the new blueprint. Go to the event graph, click and drag and highlight the 3 existing events, and press your delete key.
Bye!
Right-click and type in Draw HUD, and choose Event Receive Draw HUD. The Event Receive Draw HUD receives the size X, the width of the screen, and the size Y, the height of the screen. We'll use these to calculate where to draw the crosshair. Let's add the code that's going to draw the crosshair, and then we'll do the math to figure out where to draw the crosshair. Right-click and type in Draw Texture, and choose the Draw Texture node. For the asset, click the drop-down and select Crosshair. Let's click the Browse button to go to the content browser location where the crosshair is to look at the graphics that's there for just a second. Hover over the crosshair. Notice that the dimensions of the crosshair are 36 pixels by 36 pixels. We'll need this information to figure out where to draw the crosshair exactly. Let's go back to the HBP crosshair. Observe that the screen X and screen Y values for the Draw Texture node are floats. The size X and the size Y are integers. We'll need to provide floats to provide the location of where we're going to draw that crosshair. So we'll need to somehow convert the ints to floats. Let's do the X-axis first. We'll take the size X parameter, and we need to divide that by 2. Notice that when we press divide, we only have an option to divide an int by int, and the result of that would be an integer. We need to come up with a floating point value. We could convert it, but we can also make use of the fact that instead of dividing by 2, we can multiply an int by a float and use 0.5 for the other operand. That's the same as dividing by 2. That gives us a floating point value. Let's promote that to a variable by right-clicking on the product of that. Select Promote to Variable, and type in Crosshair.
Yeah, we already encountered this problem. Where to pin, float, but then that doesn't work. How do I get it to... I don't want to convert it. I want to... Well, fine.
Let's promote that to a variable by right-clicking on the product of that. Select Promote to Variable, and type in Crosshair X, and we'll set that. Now, we had previously observed that the texture for the crosshair was 36 pixels by 36 pixels. Let's set that in the Draw Texture node. So we'll set the screen width to 36, screen height to 36. The texture U is the texture space U coordinate of the upper left corner of the quad. We'll leave that at 0. Same with texture V. Now, texture U width is the texture space width of the quad in a normalized UV distance, meaning that 1 would be the same as the width of the texture. It's normalized. So the height would be 1 as well. Now we have to account for the fact that this texture is drawn taking into account the upper left corner of the texture being its point of origin. So if we drew that at exactly halfway across the screen, it would still be offset by half the width of the texture. So we need to subtract 18, half of the width, from the halfway point across the screen. Let's drag off of the crosshair X value, type in minus float, and 18. The remainder of that becomes our screen X value, exactly in the center of the screen. We'll hook up the set crosshair X in just a second. We need to account for the Y value as well. Now, for the Y value, we're not going to plot it halfway down the screen. We want it only a quarter of the way down the screen. But we're going to change that when we change from first-person view to third-person view and third-person view to first-person view. So that needs to be a variable. Let's add a variable by clicking the Add Variable button. And let's name this the crosshair Y location. And we'll need to change that to a floating point value. Click Compile. Let's provide a default value of that of 0.25, or 1/4 of the way down the screen. Then let's drag out the size Y, multiply, and we'll use int times float and get the crosshair Y location as the desired location of where we want the crosshair to go. We want it to go a quarter of the way down the screen by default. Let's promote that to a variable. Right click on the product of that, promote to variable, and we'll call that crosshair Y. And we're going to connect the crosshair X set value into that. And finally, we'll hook that up to the draw texture, but we have to subtract 18 from that value because half the height would be 18. I'm just going to duplicate this one by selecting it, hitting Control.
Hmm.
W, hooking that up. So crosshair Y minus 18 becomes our screen Y value. Let's try to neaten that up just a little bit. And there we go. That's the code to draw
Crosshair X. That goes there.
the HUD. Compile and save, and then close out of the HBP crosshair. Let's go back to the Blueprints folder. Notice that we left the BP base block and the BP floor in the Blueprints folder, and we did create a separate folder for blocks, so let's move those. Click on the BP base block, drag it over the blocks folder, release, and select Move Here. Do the same for the floor. Right-click in the content browser, select Blueprint class. We can close the All Classes list, and find Character for the parent class. Name the new blueprint BP underscore block player, and then open it. Make sure class defaults is selected. Let's open that up a little bit so we can read this better. And in the use controller rotation yaw setting, I'm going to move that split over a little bit. Use controller rotation yaw, we want to uncheck that. Select the mesh, and then in the skeletal mesh dropdown, choose the SK underscore block character. We're going to need to reposition this somewhat. So let's set the location. In the x-axis will be 0, the y-axis will be 0, and the z-axis will be negative 87. Then we'll change the rotation of it to 0, 0, and 270. For the animation mode, make sure Use Animation Blueprint is selected, and then from the Anim class dropdown, search for Block Character Anim BP. And there we go. We've got a nicely animated character ready to go. We'll need to add a spring arm component. So select the capsule component so that the spring arm will be parented to the capsule component. Click on Add Component and type in spring arm. And for the location of the spring arm, set it to 0, 0, and 50 in the Z. And the spring arm is what we're going to hook the camera to so that it follows the character around. The target arm length should be 300, and then find the use pawn control rotation, and make that true. With the spring arm selected, add a component and type in camera, and this camera will be parented to the spring arm. We're going to make quite a few adjustments to the character movement component. To do this, select the character movement component in the component list, and we're going to search in the details panel for these settings. Type in gravity, and we're going to change that to 1.9, and this will make the character a little more responsive, and it'll feel a little more realistic when we're running around. So we'll set that to 1.9, and for the walkable floor angle, we're going to set that to 46, and that's so we can go up the stairs static mesh that's provided with the learning kit. We're going to change the maximum walk speed to 800, and then find the jump Z velocity, and we're going to change that to 800 as well. Search for the braking deceleration flying, and set that to 500. And again, this is going to help the character when it moves around. It'll just look a little more realistic and feel more realistic.
Oh, I spelled it wrong. What did they say? 500?
As you play the game. For the rotation rate, change the Z value of that to 540. Look for orient rotation to movement, and we want that to be true. And finally, can fly, so that our character will be able to fly, and we want that to be true as well. Once you've made all those changes, you can clear out the search, press compile and save, and the next thing we're going to do is set up the inputs for this character. Go to the edit menu and select project settings.
Oh, this is
From the list
going
on
to
the
be
left, find the input section.
very
Now
different.
you'll see that there are a number of action mappings and axis mapping.
Okay. Actually, this is an older version, so it's possible that it might not be deprecated here. Yep. Okay, they already are. Okay. Let's see if I can remember how to do this. I thought that was a general overall input action thing.
Things
But...
already set up for us. We just need to add a couple of action mappings and one axis mapping. So let's start with the action mappings.
Well, I guess they've already got everything set up, so we should probably use what they've got. I would like to reiterate my learning on did I go to editor? Oh, I went to editors, not to 20. It's like, this isn't right. Okay, where did you go? Action mappings, okay.
Click the plus sign next to action mappings and name this place block. And this will be the place block action when we want to put a block down. We'll change that to the left mouse button. And we're going to add one more action mapping. And that will be the remove block. And we'll use the right mouse button for that. For the axis mappings, we need to add the axis mapping for moving up when we fly and conversely moving down. So for axis mappings, click the plus sign and type in move up for the name. And we're going to need two of them, one for going up and one for coming down. So click.
What? Oh, is it? No. Jesus Christ. How long is this? Oh, Jesus Christ, I am not close all of those.
One and only Stormy Fatten one critters. Hayes use Christo.
Advanced show. Oh, I don't have this. Okay.
Fly and conversely moving down. So for axis mappings, click the plus sign and type in move up for the name. And we're going to need two of them, one for going up and one for coming down. So click the plus sign next to that. And for the first one, we'll type in spacebar. This will be how we'll move up. So it will have a scale of 1. And to go down,
One
use
and
the
only
left
Stormy
shift.
Fatten 1 critters. Hayes use Christo.
Stormy.
And that will have a value
Left shift.
of -1, or the opposite of up. That's it. Go ahead and close out of the project settings. Back in the BP player's event graph, let's
Silly Stormy.
add the events for the movements that we're going to program. So we'll search for jump, and we want the action events, and we want the jump action event. BP player's event graph, let's add the events for the movements that we're going to program. So we'll search for jump, and we want the action events, and we want the jump action event. Right click again and search for move forward, and again we want the axis event for that
Action
one.
Events.
Right click and search for move.
It's not right. Jump. Action. Oh, there it is.
And search for action event. Right click again and search for move forward, and again we want the axis event for that one. Right click and search for move right, and we want the axis event. Right click, turn right, and the axis event for turn right, and finally for the look up, and the axis event look up. So the easiest one is jump. Let's take care of that one first. Just drag off pressed and type in jump and choose character jump. And when released, stop jump. Stop jumping. That one's done. So let's drag around all of that and place a comment and call that jump. The next one's, and let's drag around all of that and place a comment.
I don't remember how to do that. Create comment for section. It doesn't give me a clue on what it is, but okay.
And call that jump. The next ones we'll do are turn right and look up. These are fairly easy as well. So for turn right, we're going to add controller yaw input. We're turning and we're turning around the z-axis, and we'll use the axis value for that. And for the look up, we're going to add controller pitch input. And again, we'll use the axis value for that. And those axis values are 1 or -1, and they will go in the appropriate direction. So let's highlight those, select those, hit C, and we'll call that mouse input, or we'll leave a comment, mouse input, look up and turn. And we'll move those out of the way. And the last ones we have to
Thank
add
you for
are the
telling
move
me it
forward
was
and
C.
the move right. So for those, what we're going to do is we're going to get the control rotation from the pawn, and that returns a rotator. We only want to rotate around the z-axis though. So we're going to right click on that return value and split the structure pin and not use the X and Y rotation. We'll only use the Z or the yaw. And we'll actually right click and we'll type make rotator, and we'll leave the X and Y zeroed out and just take the Z or yaw of that rotation, and that'll zero those out. From this new rotator, we'll drag off of that and we'll get its forward vector, which is the direction that rotator's facing, and then we'll drag off of it again and we'll get its right vector. That's the direction to the right. And from those, we can just add movement input. So we'll right click and select add movement input. So we'll get its right that rotator's facing vector, which is the direction that rotator's facing. And then we'll drag off of it again and we'll get its right vector. That's the direction to the right. And from those, we can just add movement input. So we'll right click and select add movement input. And we'll duplicate that, as we're going to use it in both places, and look up the move forward. For the direction will be in the forward vector, and the scale value will be the scale value of the move forward input axis. This will be facing to the right of the character, so if the character is moving right, we'll hook that up to add movement input. We'll use the right vector for that, for the direction, and then again the scale input. And that's it. Our character can now move, but we haven't told the game to use our character yet. Let's compile and save, and then go back to the editor, and we have to add in our game mode next. Creating the game mode's pretty straightforward. In the blueprints folder, we'll right-click, we'll select blueprint class, and for the parent class, we use game mode base, and we'll call this GM underscore block game, or game mode block game, and open that up. We're just going to make some settings changes over here in the class defaults. For the HUD class, click the dropdown and select our HBP crosshair. And for the default pawn class, click that dropdown and find our BP block player as well. Compile and save, and we're done with the game mode. Close that out. Back in the editor, we'll need to edit the world settings. If you don't see the world settings here, go to the window menu, and in the window menu, about halfway down, you'll see world settings. And if that's unchecked, just click on it, and you can then edit your world settings. In the world settings, we're going to override the game mode to use our new game mode that we just created. So click that dropdown and find the GM game mode block game and select that. We can now test this by clicking the play button, and you should see the character appear. Now, one thing I noticed when I pressed play was that the camera wasn't positioned correctly. To fix that, go back to the BP block player and select the camera, and you'll notice that the location for the Z-axis is set to -50. I believe that's because the camera was added as a child to the spring arm. Set to the camera. To fix that, go back. I noticed one, and you should see, we can now test this by clicking the play button, and you should see the character appear. Now, one thing I noticed when I pressed play was that the camera wasn't positioned correctly. To fix that, go back to the BP block player and select the camera, and you'll notice that the location for the Z-axis is set to -50. I believe that's because the camera was added as a child to the spring arm, which is what we want. So let's zero that out. Let's click the little reset to default to set the location of the camera to 0, 0, 0. And we can go back and try it again, and I think you'll see that the camera is positioned correctly. And now you can use the crosshair to click on blocks and add blocks. If you can use the crosshair to click on block.
I see no crosshair. Okay, so we are getting that. Oh. Hello. Ratio. That's not right. Point 5. Still no. Turn inf. Neat. Show. 640, 640, 640, 62. Let me guess I didn't set this value. No, it's 0.25. Float 720. Why are you coming in as inf? What? Crosshair by location. Inf. .25. Okay, that was weird. It's not the first time I've seen some unexplainable oddities. I really just don't understand. Okay, so we still don't have some of our pin. 0, 0, 0, 0, 1, 2.
Hooking that a little bit. The HUD. P crosshair.
Okay, what did I get wrong? X 0.5 set crosshair X 18 to screen X Y crosshair X crosshair Y location. Oh. Oh. There we go. Much better. That's slightly higher than theirs was, but
For the character, so if the character's moving right, save, and then go back to the game.
making mistakes is actually a good way to
Go to
learn.
the window menu, and in the window menu, about halfway down, you'll see world settings.
Yeah, we're
Block player
past it.
and crosshair to click on blocks and add blocks if we had the ability to add blocks, which we don't have just yet, but we'll have it in a moment. The last bit of setup for the BP block player is to capture the crosshair HUD in a variable so that we can use it later. We're also going to need a player controller later, and we'll make a variable for that. So go back to the BP block player, and in the event graph, right click and type in begin play. We're going to get the event begin play node back because that's where we can capture our variables when the object is first created. So type in get player controller, and we're going to store that in a variable. So we'll right click the return value of that, promote it to a variable called player controller. And from the player controller, we can get the HUD, which returns a generic HUD object, and we'll cast that to the HBP crosshair that we previously created, as we know that's what type of class it is. I'm going to move these over a little bit. And right click on the return value of that, promote to variable, and we'll name that crosshair. So that's the setup. Let's highlight all of that, put a comment on it. Click on the return value of that, promote to variable, and we'll name that crosshair. So that's the setup. Let's highlight all of that, put a comment on it. Begin play. Be good if we could see that. There we go. Click compile and save. And finally, let's test out our character. Come back to the block game map, click play. And you see we have a character that we can move the view around with the mouse. Move the mouse left and right, up and down. We can look up, we can look down. And finally, with the W, A, S, and D keys, we can run around our map. And very shortly, we'll be able to place blocks down. In this module, we created the HUD that displays a crosshair. We added some player inputs and created a player character. Finally, we wrote the blueprint code to respond to the inputs. We also told the game to use our new player character by creating a game mode. I'll see you in the next module. The place block functionality is probably the funnest part of the project. It's where everything comes together to make an actual playable block game. Our objectives for this module are to create a custom event to place blocks. We'll apply world location and a forward vector to establish beginning and ending locations in 3D world space, utilizing a very important bit of functionality called a line trace. Finally, we'll write code to create blocks at the location the player clicked on. To get started, let's open up the BP block player. We're going to need a variable that tells us the maximum distance will allow a player to click to add a block. Click on the Add Variable button and name the new variable furthest distance to click. Change the variable type to a float. Click Compile and set the default value to 1000. That'll mean 10 blocks away from the player. Now we're going to need to write 2 pieces of support code before we get to the point where we can actually place down blocks. The first is a function to determine where the crosshair is pointing in 3D space. The second is a timeline that we'll use to rotate the player so they're facing the spot where the click occurred. Let's write the function first. Click the Add Function button and name the new function getCrosshairLocation. Add an output called crosshairLocation of type vector. Click the new parameter in the output section, change the name to crosshairLocation, and change the type to type vector. What we're essentially doing here is converting the XY value of the crosshair to a point in 3D space. To write this function, we'll need to get the crosshair and retrieve the crosshair X and Y value from the crosshair. So drag off of the crosshair and type in crosshair, get crosshair X, and crosshair Y.
Wait, what?
Next, we'll need the player controller variable, Y, get crosshair X,
Oh, got it. I'm sure.
and crosshair Y. Next, we'll need the player controller variable. And from the player controller variable, drag that out and type in D project screen to world. This node takes in a screen position and outputs a world position and direction. Perfect. The screen position is a point structure, a vector 2D structure. Let's right click on it and split the structure pin. Connect the
Oh, it had. That's it.
crosshair X to position X, crosshair Y to position Y.
Wait, what? Oh, I see. There we go.
I'm going to move all of this over. We'll take the world direction and we need to add to that the direction that the camera is pointing and the distance that the camera is back. So we'll need the spring arm, and from the spring arm, we'll get the target arm length, and then we'll add that to the furthest distance to click variable. So get that, drag that out, and from the furthest distance to click, add a plus float, hook those together. So this is to account for the fact that the camera is actually back a certain distance. And from the world direction, we're going to drag out of that type times, and we want to multiply that world direction times a float. We'll take the world position, add that, and that's going to be a vector plus vector. The second vector, and that's going to be a vector plus vector. The second vector is the product of this multiplication. And that will be the crosshair location that the player clicked on in 3D space that will be returned as a vector. Click compile and save. The get crosshair location function uses some pretty straightforward math to figure out where the crosshair is in 3D space. It's useful to break it down and learn how it works because you can apply these concepts and save. The get crosshair location function uses some pretty straightforward math to figure out where the crosshair is in 3D space. It's useful to break it down and learn how it works because you can apply these concepts in other scenarios in your game programming. The get crosshair location takes the location of the crosshair in 2D space as it's projected on the camera face. So that would be a location about right where my mouse is right now. That returns the crosshair X and Y, and it sets the screen position X and Y in the call to the dproject screen to world. The dproject screen to world returns the world position of the camera face, or the crosshair on the camera face, and the world direction as a normalized vector, which we'll see in just a second why that's useful. In this example, the camera is pointing forward in the x-axis. The normalized world direction would be 1, 0, 0. The target arm length of the spring arm that we retrieve from the spring arm right here is 300, usually, unless we've zoomed in or out, and the furthest distance to click variable is set by default to 1,000. We add those two together and come up with 1,300. We then multiply the vector that's the world direction by that distance. And the reason we use the furthest distance to click and add to it is because we want to click somewhere out here. So we multiply 1,300 times that world direction, and we come up with 1,300, 0, and 0. The product of that multiplication is then added to the world position of where the camera was. So if the player is at 200, 400, 100, or more accurately, if the camera is at that location, we then add the product that we just calculated below to that. So we add 1,300, 0, and 0 to it, come up with a location of 1,500 in the X, 400 in the Y, and 100 in the Z, out here somewhere. Now, just looking at the nodes and running the numbers by is all well and good. It would help to see this in the engine. What I've done is I've taken the get crosshair location function and duplicated it and made a debug version of it. That's right here. This version is identical to the get crosshair location function, except I've added a line trace, a topic that we'll be covering soon enough. The line trace has the ability to draw a line from the start location and the end location of the line trace, and that's going to be really useful for us. I've set up the BP block player so when we left click to simulate placing a block, it will call the get crosshair location debug function. Again, this will make more sense when you start adding the ability to add blocks, but I wanted to show this example before we got to that. Another change I made in the BP block player is that I changed the camera so that the mesh won't be hidden in the game, so that we'll actually see the camera mesh. Over in the block game map, I'm going to play the game. I'm going to move the camera up so it's pointing to a location just in front of us, and I'm going to left click. And you can see the line trace was made there. Now I'm going to press F8 to eject from the player and move out of the way here so that you can see the camera and see the line trace that occurred. So this is the location.
Mirror line trace can be used to trace lines. Silly mirror.
Where the crosshair was calculated.
Boop, boop, boop.
This is roughly our spring arm length, plus the 1,000 units. Adding all of that in the direction that the camera was facing lands just in front of us perfectly. I hope that helps you understand the code that's in the get crosshair location function. Close the get crosshair location function and find a nice blank spot to add some code. We're going to put the second piece of this together, and that's going to be a timeline that's going to rotate the player to face where the block is added. So right click and type in add timeline, and name this timeline rotate timeline. Double click on the timeline and then add a float track. Name the track alpha. Set the length of the timeline to 0.2 seconds. Shift left click at the 0 mark to add a keyframe, and you can edit that. So go up and set the time to 0 and the value to 0 if it wasn't set correctly. And then shift left click over at the end and make sure the time is set to 0.2 seconds and set the value to 1. So this value is going to go from 0 to 1 in 0.2 seconds. And you can click the zoom to fit horizontal and zoom to fit vertical so you can get a better view of that. Go ahead and click zoom to fit 0 to 1 in 0.2 seconds, and you can click
Oh, okay. Cool.
the zoom to fit horizontal and zoom to fit vertical so you can get a better view of that. Go ahead and close out of the timeline. And we're going to need two variables that we're going to change from one to the other, and they're going to be rotations. One will be the current rotation, or the rotation that the character has, and the other will be the target rotation, the rotation where we want it to be pointing. So let's add those variables. Click the Add Variable button and call this current rotation. And we're going to set these later, so don't worry that we haven't set them yet. And we want to change that type to a rotator. And click Add Variable again, and this is going to be the target rotation. That should already be a rotator. Go ahead and just click Compile. Again, we'll set these values before we use the timeline. So let's get the current rotation and get the target rotation, and we'll use the alpha value to interpolate between the two. And we'll use what's called a lerp for a rotator. So drag out of the current rotation and type in lerp for linear interpolation and set the target rotation as B. So current rotation is A, target rotation is B. Alpha is how far between A and B we are. And at 0, we'll be on A, and on when alpha is 1, we'll be at B. So we'll use the alpha value to go between the two. And in the update of the timeline, we'll drag off of that. We'll type in set actor rotation. Now we don't want to set the entire rotation. We just want to rotate around the Z-axis. So we're going to split the return value, split structure pin, and just get the yaw and right click on the new rotation and split that structure pin. We'll zero out the X and Y and just use the yaw for that. And let's select all of that, move it over a little bit, press C to add a comment. Timeline for rotating before placing block. And that's it for the timeline. All right, so now we're ready to add the functionality to add a block. Let's find a nice open area in the event graph to get some room to write for placing block. And that's it for the timeline. All right, so now we're ready to add the functionality to add a block. Let's find a nice open area in the event graph to get some room to write some code, and right click and type in place block to get the action event place block. And what we're going to do is we're going to do this in several steps. We're going to write a custom event to actually place the block and have a timer that's called when the place block event occurs. So in other words, when they left click. So let's right click and type in add custom event and name this place block down. Drag off of the pressed execution wire and type in set timer by event. Set the time to 0.2 seconds, and we want that to loop. Hook up the event delegate to the place block down. Now, we also have to call this directly, otherwise it'll be a delay. There will be a delay of 0.2 seconds. So drag off of the set timer by event and type in place block down to call that immediately so we can start placing blocks. Now, one very important thing we have to do here is stop calling this when we release the left mouse button or whatever button we've assigned to place blocks. So off of the released execution pin, type in clear timer by function name, and the function name that goes here has to match the function name for the custom event. So to make sure that's correct, what I do is I select the custom event, press F2 as if I were going to rename it, Control C to copy, click here in function name, and Control V to paste, and that avoids any possible typos. V to C to copy, press F2 as if I were going to rename it, Control C to copy, click here in function name, and Control V to paste, and that avoids any possible.
Interesting. It's kind of a nuisance.
Typos. So we are all set, and we just have to write the code to actually place the block down. So to do that, we're going to first rotate the character in the proper direction, and we'll do that by right-clicking and calling.
I don't like this at all. This feels extremely dangerous. Because if somebody comes in and renames this method, then it'll never stop. Because they're not coupled together. I don't like that. But I have no idea. Can't imagine that there's an easy way to do that. What's that called? Get custom event name, maybe? Event name. That's XX stuff. Alright, so let's back up and see if there's a clear timer by function name. Set timer by event. You know, I remember somebody yesterday had mentioned that you really got to be careful with timers, that you have to make sure you clear them. I hadn't used them yet, so they're accurate in what they said. But how do I make this more... Timer by event, set timer by function name. Place block down. Set timer by event, so show tick event. Token set existing timer will reset the timer with updated parameters. Yeah, this just seems very dangerous. I would avoid doing this in my own code, but for moving on purposes.
And we'll do that by right-clicking and calling get actor rotation. And we'll use that to assign the current rotation. So do a set on current rotation, look that up, and the current rotation of the actor is now set. Then we'll get the actor's location, right-click, get actor location, and we'll get the actor's...
Place block down. Oh, I see. Okay. Set. Current rotation. I'm gonna figure out what I'm gonna do. Now I'm gonna figure out if I'm gonna finish all of these tutorials tonight or not. I don't know. We'll see. Actually, let's do that. Let's yeah. Alright, we're looking at least an hour and a half just of the just of the videos alone, and I know that I'm slower to go through them. Although I am... Yeah, no, it's still... Alright, I'll at least finish the video that I'm on. Placing blocks, review... Oh, okay, this actually is a good spot. Place the blocks, review the basic list. So this is going to be a review spot. So... Okay. I think we might do the number 6 here. And we might stop there for tonight.
Locations, and we'll use that to assign the current rotation. So do a set on current rotation.
We'll see.
Look that up, and the current rotation of the actor is now set. Then we'll get the actor's location, right-click, get actor location. And from that, we'll find what direction they are looking. So drag off of that, find, look at rotation. And then we'll use our get crosshair location function. So we'll have to call that, and that will return the crosshair location. And we'll use that to set the value of the target rotation. So drag out the target rotation, and we're going to do a set on that. And hook up that execution pin. Now that we've set our current rotation and our target rotation,
This... What'd you come off of? Set current
drag out the
rotation.
target rotation, and we're going to do a set on that. And hook up that execution pin. Now that we've set our current rotation and our target rotation, we can use the timeline that we created earlier to rotate the player to that location. If you open up the components in the variables, you'll see that the rotate timeline is a variable that you can get. Drag that out, get it, and now we can call functions on that timeline. So from the rotate timeline, drag that out and type in play from start. That will play the timeline for us, rotating between the current rotation and the target rotation. Drag off of that, and we need to now figure out what block we clicked on. And we don't have a function for that yet. We have to write it. So that's the next step. Click on the add function and type in get clicked on block. The get clicked on block function has to do a bit of work to figure out what block was clicked on. It's going to need some information to know where its target is, and it's going to return that back as a block that was clicked on or the fact that a block wasn't clicked on. So we'll use inputs and outputs for that. For the input, we're going to add a new input parameter. So click on new input and name that target, and that should be a vector. And if you don't have that, then change the type to vector. The outputs for this function are going to be whether or not the hit was a success, where the location was, what the normal was, the direction the block was facing, and the block that was actually hit. So click on new parameter, and for output, new parameter, and we're going to name this one hit success. That's going to be a Boolean, true or false. Did we hit something successfully? Click new parameter, and we're going to name this one location. Where did the hit occurred? That should be a vector, and new output parameter again. And the normal, what direction was the face facing that was hit? And that's a vector as well. Finally, we'll click new parameter and hit block. If hit success was true, hit block will be set to a reference to the block that was hit. So we're going to change the type of that to a BP base block. Now, because we're using inheritance, we can use a BP base block and return the BP base block that was hit, no matter what kind of block was hit. A child class of a BP base block could be hit. It can still be a BP base block because inheritance supports that. So there's our return node for that. Now we're going to need a second return node in the event that hit success was false. And you'll see why when we write this function. So I'm just going to select the return node and hit Control W to duplicate that. And we'll get to that part in just a couple of minutes here. So
why does he say Control W? That is not the right key. How about Control D? Control W is close. It's like telling someone to Alt F4.
Perform is what's called a line trace. And a line trace needs to know where to start and where to end in the world in 3D space. And then it will tell you what it hit along the way. So let's right click and type in line trace by channel. And we're going to hook the execution pin of the function into that. And we need to have the start and the end location. So the end location is the target, where to end the line trace. And that's actually where the crosshair is. And we figured that out back in our event graph. We'll furnish that when we call this function. We need to know where to start though. And we're going to start from the camera. Drag out the camera, and off the camera, we're going to get the world location, and that will be our starting point for the line trace. Now, the line trace is going to return a lot of information. So rather than return all that information, we're returning parts of it. What we're going to do is we're going to take the out hit structure and we're going to break that apart and only get the parts that we need. So if you drag out hit out and type in break hit result, you'll get a break hit result node. I'm going to expand that and you can see all the information that you get from that. We'll use the return value to determine whether or not the line trace actually hit something. So put in a branch, hold down your B key and left click and hook up the return value to this condition.
Okay, that's cool.
Hook in the execution wire to the branch. So if we actually hit something, we're going to return this node, which is going to have all the information on the stuff that we hit. And the hit success variable or return value is going to be true. If we didn't hit something, the false pin will run. We're going to return that and the hit success will be false. The information that we need is going to come from the hit result. So the location gets hooked up here. The normal gets hooked up here. And the block that was hit is going to be the hit actor, but we're going to cast it first to a BP base block just to be sure it was a BP base block that we hit. So drag off of the hit actor and type in cast to BP base block. And we're going to hook that into the true. And we need to re-hook that up there. And for the if that cast failed, if we didn't hit a BP base block, but we hit something else, then that cast will fail. And that will go to our return node as well. So we have two possible returns. The nice thing is now that we have a BP base block, we can return that as our output. You can close up the break hit result by clicking this up arrow, and we only have the nodes we need. And that's it. This function will determine whether or not we clicked on a block and it will return the block that we clicked on. Let's compile and save and then close the get clicked on block function. Back in the event graph, now that we have save and then close the get clicked on block function and then close the get block that we clicked on. Let's compile and save and then close the get clicked on block function. Back in the event graph, now that we have a get clicked on block function, we can drag off the exec pin from the timeline, type in get clicked on block, and call our function. Now we need to have a target. Where are we looking at that to find out where we clicked? And that is the crosshair location. So we're going to connect that from there to there, and that's quite a stretch. And you can use a reroute node to neaten that up by double-clicking on the wire, dragging that down, double-clicking, dragging that to connect that from there to there, and that's quite a stretch. And you can use a reroute node to neaten that up by double-clicking on the wire, dragging that down, double-clicking, dragging that down, like so. So now that we've got a clicked on block, we need to check whether or not the hit was a success. We can hold down the B key for a branch, hook that up, hook in the hit success. And if it was successful, the true wire will run, and we're going to get the attach location of this block. So because this hit was a success, that means that we hit a BP base block, and we have a BP base block here. We can drag out of that and call its get attach location that we wrote quite a few modules back. We can pass in the location and the normal, the 2 bits of information that that function needs, hook up the true wire to that, and we'll have our attach location right here. Let's drag out our mesh of our character and play an animation. So we'll drag out the mesh and we'll type in play montage. And for the asset to play, select the block character interact quick montage. Change the play rate to 3, which looks better, it's quicker, and hook up the get attached location to that. When that montage blends out, we'll spawn the block. So on the on blend out, type in spawn actor from class, and we're going to choose the BP base block because we don't have specialized blocks yet. So we'll just start with a BP base block. And that's going to need to know where to spawn that actor. Right click on the spawn transform and split that. And from the get attached location, blocks yet. So we'll just start with a BP base block. And that's going to need to know where to spawn that actor. Right click on the spawn transform and split that. And from the get attached location function that returns the location of where to spawn that, hook that into the spawn transform location. Also change the collision handling override to do not spawn so that it doesn't spawn a block on top of us if we're too close. Let's click compile. Let's click save and go back to the block game map and press play. You should be able to left click on the floor.
Mario, yes, move those boxes around. Take that information out of the animation. It's awesome. Just move those assets. Silly. I gotta AFK a minute. Okay, 13 minutes.
Block and spawn so that it doesn't spawn a block. It's the collision handling override to do not spawn so that it doesn't spawn a block on top of us if we're too close. Let's click compile. Let's click save and go back to the block game map and press play. You should be able to left click on the floor block and place blocks and notice that animation playing when that occurs. You can also click on existing blocks that you added and place blocks, and they should spawn in the correct location. Additionally, note that the player will turn. So when I click to the side, the player rotates to the proper location where the block is.
Alright, let's see if I did all that right. More pointedly, let's see what I get wrong. I forgot what the place was. Where did we say the place was?
And place floor block. You should be able to left click on the floor block
Left click.
and place blocks and notice that animation playing when that occurs. You can also click on existing blocks that you added and place blocks, and they should spawn in the correct location. Additionally, note that the player will turn. So when I click to the side, the player rotates to the proper location where the block is.
Okay, so we're getting the rotation.
We created a custom event to place blocks. We applied world location.
But we are missing something else. So what are we missing? Okay. 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 Target crosshair location. Click block. Success is coming across as false. So, why are you false? That's coming across as true. Oh! Wait, hit true is out. When did... This needs to be true. They must have set that and I missed it. Easy. See, now I'm glad that I watched the debugging tutorial. So now I know how to fix stuff like that. And look, now it works. I make all the blocks. Oh, I can only go out to 1,000, so can't go that far out. I make other blocks. These other blocks. So many blocks. It's definitely a weird rotation thing going on. So like the character rotation thing, they're spinning around and awkward. I I understand the reason why. I don't know how to fix it yet, but I know why it's happening. We're over the edge of the world. Yeah. Okay. Yeah.
Location and a forward vector to establish a beginning and ending location in 3D world space for the line trace. And finally, we created new instances of blocks at the correct location. We're well on our way to building a great block game. I'll see you in the next lesson. Understanding the math behind the BP base block's getAttach location function can further put into focus how vectors are used and provide an example of one way to use a static mesh's normal values. Our objectives for this module are to explain the coordinate system which our game is built on. We'll demonstrate how the getAttach location function uses a normal to figure out which direction a face is pointing. Finally, we'll solve the question of where to place a new block when an existing block is clicked on.
Eh? Did I... Placing blocks review. Oh, okay.
Our game is built on a 3D Cartesian coordinate system, defined using an X, Y, and Z axis. To keep things simple, we've made the point of origin of the floor block snap to a grid of 100. In our system, X values increase in a positive direction moving forward, Y values increase in a positive direction moving to the right, and Z values increase in a positive direction moving up. All axes decrease in value in the opposite direction. Unreal units are 1 centimeter. Our blocks are 100 centimeter cubes. In other words, they are 1 meter cubed. We'll use these figures when we determine where blocks will go in the world. In the block game, all blocks have a point of origin in their lower left-hand corner. This is how we specify where to add a new block. We do this by providing the location of the bottom left corner of the new block in global space. Now that we know how the coordinate system is used in our game, the next piece of the puzzle is the normal. Normals on a static mesh define which direction a face is pointing. When we specify normals on the BP base block, we're indicating the values in the x, y, and z axis. Normals are normalized values, meaning they have a value between -1 and +1. If a normal's value is -1, it's pointing in the negative direction of the axis that it's specifying. If a normal's value is +1, it's pointing in the positive direction of the axis that it's specifying. If a normal's value is 0, it's perpendicular or on edge. We use a vector to specify the normal. By doing so, we can identify which face was clicked on, or more accurately, where the hit occurred with a line trace. In this version of the block game, I added some additional information to show where the point of origin of certain blocks are. For example, the floor block is showing its point of origin of x0, y0, and z0. On the block that was added, its point of origin is 100 in the x-axis, 100 in the y-axis, and since it's on top of this floor, it's at 100 in the z-axis. The normals on the faces are shown on this specialized block as well. On the face that we're looking at, it's facing in the x-axis in the negative direction, so its x value for the normal is -1, and it is 0 for the y and 0 for the z. On the opposite side of that block, notice that the x value is 1, and the y and the z are both still 0. On the y side, we've got an x of 0, a y of -1, since it's facing in the negative y-axis, and a z of 0. And on top of the block, we see that we've got an x and y of 0 and a z of +1. Observe when we place another block, we get the new coordinates shown on the block, and the x-axis, we're at 300, here's 0, 100, 200, 300 in the x, 300 in the y, so there's 0 in the y, 100, 200, and 300, and we're still at 100 in the x since we're on top of this floor block. If we add a block on top of that, the x and the y stay the same, and the z goes up to 200. When we add one on top of that, we should see a z of 300. Back to the getAttached location function in the BP base block. This function receives two vectors as parameters: the location of where the crosshair was when the player clicked, and the normal, the direction the face that was clicked on was facing. Both of these parameters are vectors. This means that they both contain an x, y, and z value. As an example of how the function works, let's use the floor block at 100 in the x, 200 in the y, and 0 in the z, and work out what happens when a player clicks on top of that block at the location 153 in the x, 229 in the y, and 100 in the z. The cursor in the graphic on this slide approximates that location. The normal value will be 001 because the face that was clicked on is facing in the positive z direction. It's facing upwards. The first node adds the two vectors together, which sounds more complicated than it is. It's just straightforward addition. The x values are added, the y values are added, and the z values are added. In this case, the sum would be 153, 229, and 101. The next node subtracts 50 from the sum of the previous node. Again, it sounds more complicated than it is. This simply subtracts 50 from each of the three axes. The remainder of this subtraction would be 103, 179, and 51. The next node snaps the remainder of the subtraction to a 100-unit grid. This rounds down any axis that's 50.0 or below to the nearest 100, and rounds up any axis that's greater than 50.0 upwards to the nearest 100. The result of this is a vector snapped to a grid that is a vector that defines the attachment point for the next block. 103, 179, 51 would snap to 100, 200, 100. Once again, using a slightly modified version of the game, I've added a cursor that shows where the next block would be if you were to click. And you can see that the math is fairly straightforward. When we are at 0, 0, 0, and we put the cursor right on top of that block, the only axis that's going to change is the z-axis. We're going up 1 whole unit, or 1 meter, or 100 centimeters, and if we click and add that block, we'll get a block at x0, y0, z100. The math works no matter which side or which face we click on. And you could see that it's very fast and very accurate. To wrap things up, the math behind the getAttached location function is straightforward. It's addition and subtraction. Using vectors is also straightforward. Vectors are a structure with three values, an x, y, and z. Adding vectors and subtracting singular values from them involves applying the operation to each axis and obtaining the result. Having a good grasp on the 3D coordinate system and a concept such as normals can help you solve more complex problems in the future. In this module, we explain the coordinate system in which our game is built on. We applied the 3D Cartesian coordinates and surface normals as a means to determine which side of a block was clicked on. We determined where to place a new block when another block is clicked on.
Okay. So I think I'm going to go ahead and call it here. Thanks everyone for hanging out as always. Be well, be safe, be yourself, be kind, be all the good things. And have a great rest of your day.